4.10, the antiderivative. And what is that? The antiderivative is the reverse of differentiation, as the name implies. For example, let's look at the definition on page 485. A function f is an antiderivative of the function small f if the f prime of x equal to f of x for all the x that we care about in the domain. That is, if f, there's a function big F, right? And there's a function small f. If the condition satisfies that f prime of x happens to be equal to the small f of x, then this is the big F is called the antiderivative of the small f. All right. As an example, of course, we can think about small f equals to 2x. Now, what kind of function can you imagine whose derivative will become 2x? Now, if you use your imagination, like Walt Disney wants us to do, Walt Disney, and then you will quickly remember that x squared, when you take the derivative of x squared, that would become 2x, right? And you are right. X squared would be the antiderivative of 2x that we're looking for. However, now, okay, so the next question is this. Now, given the antiderivative, let's see that we, okay. Now, the question then is, okay, that's a nice antiderivative. Are there other antiderivatives? And the answer is yes. For example, if you have x squared plus, say, 1, the derivative of x squared plus 1 is also equal to 2x, right? In general, because the derivative of constant is 0, in general, x squared plus any constant, positive or negative, the derivative will always be 2x. Therefore, the antiderivative is the function plus any constant, okay? That it will all work. It's called a family. The family of antiderivatives is stuff that add any kind of constant will work, simply because the derivative of constant is 0. So you get knocked out during the derivative process. So when you crank it backwards, then you can add whatever constant you want. Now, next, how about anything else? Is there anything that doesn't look like x squared plus c, but whose derivative will also be 2x? And the answer is no. Look at the bottom of your of the page, where we are going to quote Corollary 2 of the mean value theorem. Now, did I write down did I write down Corollary 2? Yes, the Corollary 2 of the mean value theorem is on page well, I'll just read it to you. It's on page 386, Theorem 4.7, Corollary 2, Constant Difference Theorem, which said if f and g are differentiable over an interval I, if f prime equals to g prime the whole time, okay, then f equals to g plus some constant. That's what Corollary 2 says. Well, we proved that some time back, right now. So right now we're just going to believe it and not worry about proving it again. So in other words, Corollary 2 says if two derivatives of two functions are the same, then the two functions are only different, at the most different by a constant, which means if there is another function whose derivative is equal to 2x, then that function, it has to be only different from this function by a constant only. In other words, add another constant in there. Which means that there is no other function whose derivative is 2x except unless it's in this form, okay? Because any other function has to be different by only a constant. So having said that, let's turn the page to page 486, where Theorem 4.14, which is a repeat of Corollary 2, and which says that if big F is an antiderivative of the small f, like we said, then the function f of x, then the big F plus some constant is the antiderivative of the small f. Furthermore, any antiderivative of small f is only different from the big F by a constant. That is, this is it. Okay, that's all you need to remember, is that the antiderivative is there's only one antiderivative, except for you're able to add a constant to it. So that's the point of the theorem. To find the now that we've said that, let's find the antiderivative. Example 4.50, which I will ask you to do as homework, actually, because look at it for a moment. Part A, f of x equals 3x squared. Can you think of a function whose derivative becomes 3x squared? Now think about that, okay? I'll let you think about that. Similarly, part B, can you think of a function whose derivative is 1 over x? Strain your brain a little bit. And part C, can you think of a function whose derivative is cosine x? Yeah, think some more. And lastly, can you think of a function whose derivative is e to the power x, right? These 4 things. And so I'll let you slave over that puzzling problem, and we'll flip to the next page. The indefinite integrals. The indefinite integral is a notation. Now we're going into the notation, and we're gonna this is the first time you're gonna be introduced to this symbol right here. Okay, and which people are sort of scared of, actually. But do not be scared of it. This symbol together with this symbol means one term, which is to take the antiderivative. Okay, and it's called to integrate. This is the integral sign, and that dx is just there. The whole thing works like parentheses. Okay, so that the whole thing is stuck on the inside, but you don't need parentheses because you have two symbols, two sets of symbols that all together means take the antiderivative, which is now going to be called the integration. Now this particular object here, okay, when you stick your function to be integrated inside, this whole thing is called an indefinite integral. Why is it indefinite? Because it varies within c. You can add a c to it, and where's the c? Right here. You can add a c to it, and the end is still acceptable as the answer. So in this sense, for example, if you have an antiderivative big F, then the integral, the indefinite integral is equal to the antiderivative plus some constant. Okay, so basically the indefinite integral is the antiderivative except for the constant. Okay, the antiderivative doesn't care about the constant. The indefinite integral includes the constant to be so that we're sure that, because when you do take a derivative, the constant disappears. So then, so anything within the constant will work as the antiderivative, as the to reach f of x when you take the derivative. So having said that, let's look at something. For example, to emphasize the concept that there's a c there, let's say we want to take the indefinite integral of a simple function such as f of x, equals to 2x, okay, dx. So what is the what kind of function that goes when you take the derivative becomes 2x? Well, the answer is simply x squared, right? So that is equal to x squared. But we have to not forget the constant. When you take the indefinite integral, the reason it's indefinite is because we have to always tag on the constant. Why? Because the constant here means any number here. You can plug any number in here, and then take the derivative of x squared plus the number. The answer is 2x. That's why it's called a family. Okay, here's your family. To draw the example and to actually visualize it, see, it's not just x squared whose derivative becomes 2x, but x squared plus any old thing you can think of. See, they draw some here, and there's a infinite number of more options, right? It's just because there are infinite numbers of constant that you can put here, whose derivative becomes 2x. So that's that. And okay, now let's look at the next rule, the power rule for integrals. As you remember, the power rule says that when you take the derivative to the power n, the derivative then becomes nx n minus 1. Then so you work this thing backwards, then the integration of x to the power n, how would you integrate it? That would simply be equal to x n plus 1 over n plus 1. Why? Because if you take the derivative of this thing, right, you take that down, the n plus 1 down, and then that cancels out with the bottom, and you're left with n, just like this. See? So you take the derivative of this is equal to that. Therefore, to integrate the indefinite integral then equals to this thing. And of course, as always, don't forget that c that has to hang around. When you take the integration, yeah, the c is always there. The only difference between the indefinite integral and the antiderivative is the antiderivative you refer to just the function, ignoring the c. But we always remember the c, okay? Don't ever, then we're not going to care about the antiderivative from now on, because every time you integrate, you always tag the c along. The c just comes. No matter what function you integrate, there's always a c there. That's just the way it is. And so this is the formula for using the power rule for integrals. Now, in general, now let's look at the next page, which gives you a nice old chart of all the derivatives. Let's see, can you see it? Like that? Yeah, all the derivatives you've seen so far. And then so you crank it backwards, and that's how you take the integration. For example, we have the derivative of a constant. If you integrate a constant, it equals to constant times x. If you integrate 1 over x, the antiderivative is natural log, of course. If you integrate e to the power x, the antiderivative is still e to the power x. If you integrate cosine, what goes to cosine? Well, sine. So the answer, the integration to integrate cosine, you get sine, and so on. This is basically a list of all the derivative tricks we've learned so far, right? And out of those tricks, then we can do integration, which is actually, if you think about it, quite limited, because we can take derivatives of basically any function, because we have specific rules, and then we have rules of combining things, such as when you take a derivative of addition or subtraction, you can just take the derivative of each item being added or subtracted. Whereas if in terms of products or division, then we can use the product rule or quotient rule, right? That is not true for integration, I'm afraid. Let's see, did I? Okay. Now, for integration, you can still split things up to integrate, because when you took the derivatives, you were able to just split up, you know. And when things are added up, you can take the derivative of each object. And so the reverse process is also true. If you integrate something, a bunch of stuff added together, you can integrate each one individually and then add or subtract them together. That there is no product or quotient rule for integration, however. So if you have products or quotients, then you're completely out of luck, basically, and you have to come up with some trick that hope that it works. So remember, there is no corresponding trick rule for integration when it comes to multiplication or division. You have to come up with a better plan. So having said that, let's look at example 4.51. Example 4.51, you just have to integrate some simple equation. Okay, part A is fairly simple, part B not so simple, but you're just supposed to take the derivative and make sure that it works out. So I will let you do that as homework. And let's move on. And to the next property on the next page, theorem 4.16 on page 491, where it says the properties of indefinite integrals in terms of addition of ends and constant multiplication. As I mentioned a moment ago, when you have to add two things together, like this, okay? Let's say you have to integrate f plus g dx. Okay, now at that, or minus, doesn't matter. If that's the case, then you can simply break it up and do it in two parts if that's convenient for you. G dx. Anyway, yeah, dx. So that's and the same with subtraction, and also the same if you have some constant, because when you take derivatives, having a constant there doesn't hurt anything, and just take it right out. So the same applies for integration. You can just take it right out, f, in case of a constant. See, constants don't hurt much. And that's about it. Now let's look at the next example, 4.52 on page 492. Example 4.52, I'm also assigning it as homework, but let's talk about it briefly. The part A, you have to integrate polynomial. That goes straightforward. Use the power rule and calculate it backwards. And part B, the same thing. You use the power rule. Even though one of the power is a fraction, you just divide out the x, right? When the power becomes a negative fraction, but that doesn't change anything. You use the power rule anyway. Now, I should mention that in part B, at one point, it says that the fraction equals to 0. And you might wonder, why does it equal to 0? It doesn't. That's just a slip of hand of the author. So don't worry about that. It doesn't equal to 0, and just go ahead and perform the power rule for integration, which comes out right away. And then part C is you have 4 over 1 plus x squared. And you're like, okay, can't use the power rule here. What do we do? Then you go back and look at that chart, the big chart we saw a couple pages ago, and find where you finally find out the one down here. See, the down here where the derivative of the tangent. Can you see it? Anyway, find that thing which says the derivative of the inverse tangent, is that inverse arctan? Well, whatever it's called, is equal to that. And so you use that formula to pull out your answer. And the last part D, you want to take the integrate tangent x cosine x. And you're thinking, wow, how would I do that? Yeah, because I just said that you cannot break up things like multiplication. Okay, there is no product rule in integration. So, however, this is just a silly trick question. What's tangent x cosine x? Tangent is sine over cosine, so tangent x cosine x is just sine x. So you will integrate sine x, which means you have to figure out what derivative what equals a sine x. So I'll let you puzzle that out and do example 4.52 as your homework. And having said that, let's move on. It's something called initial value problems. Now, the initial value problems just means that, as we mentioned earlier, that when you integrate a function, you get the antiderivative plus a number, okay, c, any c, because it will work as the indefinite integral. But sometimes we might need a specific function, not just the whole family. We want one of them, okay? And to nail down that one is because we have an initial condition or initial value that needs to be met. Now, to do that, let's look at an example. Right. Such as example 4.53. Example 4.53, I will write it down here. Okay, so example 4.53. All right, so we have a very simple problem, that is dy by dx equals to sine of x, right? Equals sine of x, but they give you another initial value, which is y at 0 equal to 5. And why does that matter? What matters that value, this condition here determines what that c is going to be. In other words, they don't want you to just tell them add some constant. They want to know exactly what constant it is that will fit this condition. So what happens then, you take the derivative. You integrate this thing. If you integrate it, then we say the integral of sine x dx, that of course equal to some kind of cosine x, right? But pay attention, derivative of cosine is minus sine, so you have to stick a negative sign there. And that's about it, plus some constant c. However, so your integration is done, but now you have to take care of the detail being what c. So this point means that when x equal to 0, y equal to 5 is what y0 equal to 5 means. So when x is 0, y is 5, that means, okay, what's y? This thing is y right here, what we've been doing this whole time. All right, so if x is 0, y is 5, we will write down 5 equals to minus cosine 0, which is cosine 0 is 1, so that's negative 1, plus c, so that's minus 1. So that gives you c equal to 6, right? Yes. And therefore, the function that we're looking for with this initial condition is y equals to, copy that back down, minus cosine x plus c is, was it 6 or minus 6? I guess it's 6. All right, and that is the answer. So the initial value serves to help to make you hunt down what constant are we talking about, because we're not just using the family of functions. That's like the infinite number of choices depending on what c is, but they want just one. Okay, pick one that fits the condition, and this would be the one that fits the initial condition, that the c, when you let c equals to 6. And that's the end of example 4.53. Let's look at example 4.54. Now it is a neat little example to show how the antiderivative and the initial value, I think, works. Okay, so let's read the problem that says a car is traveling at some fixed speed, 60 miles per hour or 88 feet per second, and then the car put on the brakes. Once put on the brakes, it decelerates at a constant rate of 15 feet per second squared. It's also called 15 feet per second. Anyway, so how long did it take before the car stops? That's part A. And how far did it take for the car to stop? All right, which is a kind of an interesting problem, right? So we will go ahead and work on this. First, the car's initial velocity is initial, okay? 0 means initial velocity is at 88 feet per second. So we will be using feet and second as the standard unit, and ignore the 60 miles an hour. That's just to give you an idea what that means. 88 feet per second. So the car decelerates at, so A, which is the acceleration, all right, equals to is decelerating, negative 15 feet per second squared. Feet per second. And that's how the physics people want you to say it, I think, based on what I remember when I studied physics. Now, so there's that. And so how many seconds elapse before the car stops? So when does the car stop? The car stops when its velocity becomes 0. Okay, start here, and we know what A is. So we're going to integrate. So there's A, and then we know that dv by dt equals to A, right? So we're going to do our new trick that we learned today, which is to integrate A to get to get V. So we will take the integrate 15 feet per second, okay, dt. The variable right now we're concerned with is time, so we'll do the dt. that equals, that's the indefinite integral, and that of course equals to 15t plus something, okay, plus some constant. Don't forget the constant. And then did I say negative? Let's not forget the negative, because it's decelerating. Otherwise you're going to be calculating accelerating from 60 miles an hour, and that's not going to go over. So v, and then also with this, so vt equals to that, where v0, as we mentioned, that v0 is 88. So when so in the beginning of time, okay, as that means when t equal to 0, the v, this is v, okay, t equal to 0, v equals to 88. All right, right. So and then what do we do? Then we need to plug this in. That means v equals to minus 15, put t equal to 0, v equals to 88, which means c equals to 88. When you plug in 88 here, 0 equal to 0. Yeah, so c equals to 88, and then we get v equals to minus 15 t plus 88. All right, so this v is v of t. Okay, the variable is t. Okay, so and then, so that's pretty good. When is v going to 0? That's the question, right? We start out at 88, and it goes down by 15 feet per second, 15 feet per second each second. So well, we set vt equal to 0. So 0 equals to minus 15 t plus 88. So t equals to, that means t equal to 88 over 15. And that's about 6 seconds, slightly less. Okay, so if it's 90 divided by 15, it's 6, so it's slightly less than 6 seconds, which is fine. So the car took roughly 6 seconds to come to a stop. And what was the next question? All right, at that point, so from there, we need to figure out how far it traveled. Now this is the v of t, and the distance traveled is called s. S, where ds by dt equals to v. Okay, just like dv by dt equals to a, ds by dt equals to v, and that's the variable is t. All right, v of t. So then, so then we need to integrate this thing. So let's integrate it. If we integrate minus 15t plus 88, what is that? dt, that equals to let's see, s, right? So that equal to s, and to integrate that we get but we need the initial position. Where's the initial position? Well, in the beginning we'll call it 0. All right, so s, where s of 0 at time 0, when we count, we'll count that point as 0 and see how far it goes from that point. So s0 equal to 0. And then we'll integrate this thing, and that equals to, so s of t equals to, you raise the power and divide by the power. That's how you do the power rule. So minus 15 t squared over 2 plus 88 t. Okay, that is a constant, so you add a t to it, and then plus some constant. The constant is not important because, as you can see, when s is 0, when t is 0, the whole thing is 0, which means the constant is 0. So we can forget that. So here is the function for s of t. And then we have to plug in t equals to 88 over 15. So what is s of 88 over 15? Okay, plug that into the t. and we'll get some kind of an answer, which I'm not going to plug it in right now. So please plug it into your calculator or something, and make sure you get it right. If you don't get it right, that means you are using the calculator wrong. You're pushing the wrong button or something. Okay, you need to look over your calculator menu and make sure you get the thing right. Because I've had professors complain to me that even his students who finish calculus can't use the calculator right. It's like, how is that possible? I mean, figure out how to use the calculator. Do not let it go until you get it right. And this particular number happens to be 258, as the book has it, and I'm not gonna do that right now. And that marks the end of this section, I think. Let's see. Yep, that's the end. Now I haven't picked out the homework yet. It's not the funnest thing in the world to do, picking out homework. But so I will do that, and then but I will list it below this video, and also in the next video I will talk about the homework in the next video.